Okay, and now we get to the last talk in sort of our ZK accelerated session from Markus Schofnegger, who works at Horizon Labs and was involved in the development of the Poseidon 1 and 2 functions, which are arguably probably the most popular hash functions used when you're trying to use hash in a ZK circuit. And he's going to present, give a little bit of an overview, what's the current state with SNARK-Friendly Hash Functions, yeah, big round of applause for him.
Oh, still there. It's online. Okay, yeah, thanks for a nice introduction. Now actually I'm at Fabric, but that's very, very new still. So yeah, this talk will be slightly less technical, I guess, than the previous talks we've seen. I'll try to give an overview of this area of SNARK-Friendly Hash Functions. If you're not aware of this area, I will also give a very short introduction of why this is actually needed. And yeah, so essentially it will contain a very short history lesson, then an overview of current challenges, and also some future directions we may be able to take. Alright, so let's start right away. SNARK-Friendly Hash Functions, we all know SHA, right? SHA-2, SHA-3, 8, we all know those. And we have had those for many decades now, a few decades. So why do we need SNARK-Friendly Hash Functions? We already have hash functions. And that already brings me to the history lesson. So, and some of the things in this part are actually not true anymore. That's also part of the reason for this talk, because things have changed, right? And also in cryptography, things have changed. And this is not something that started a couple of years ago. It started already 2-3 decades ago. But it became very apparent a few years ago. We have new things. We don't have like encryption and only authentication anymore. Now we have things like multi-party computation, or even like homomorphic encryption, even post-quantum signatures. There have been many competitions also on that. I think the second one is running now. And we also have zero-knowledge proof systems, which is the main focus of this talk here. So, from the perspective of a symmetric cryptographer, we can ask ourselves the question, well, how do these things influence the design? And many of those things actually use symmetric cryptography internally. And it turns out that all of those settings have a huge impact on the building blocks you want to use in your cipher, or hash functions, or in your permutation more generally. And it turns out that some of those building blocks are really good and some of those are really bad. And we didn't know this 5 years ago. I think we have a much better understanding now, and we will get a better understanding also in the future, but it's still like an area which develops. And of course, there's the security considerations we have with those building blocks, and we'll see that it's not so easy to keep SNARK-Friendly Hash Functions secure, because many of the stuff we worked on previously in the last decades on symmetric cryptography don't work anymore. But yeah, a very short motivation. I'm sure many of you already know this. So there has been a rise of on-chain ZK use cases. Again, this is like years ago. And very generally, we have some public state or like public root of some Merkle tree. And one thing we can do is, for example, we can prove that some leaf value as a secret here is in this Merkle tree. And of course, we can do this very simply by just providing the authentication path and the leaf value. But we don't want to do this, we want to do this in ZK. And it turns out if we want to do this in ZK, then the cost of the verification, or the proving in general, is related to the circuit friendliness of the hash function we use in this Merkle tree. And suddenly, this is a situation where SHA becomes very inefficient. It's a bit different now, because we know techniques to make it more efficient, but a couple of years ago it was really inefficient. Alright, so very short, an example use case. Let us say that the leaf corresponds to some transaction or to some spending of a coin. Then we want to prove, for example, in ZK, that we actually know the hash value of that specific coin. So we know the pre-image of the hash value of that coin or transaction. And we want to prove in ZK also that the transaction is contained in the tree. And the ZK part is very, very crucial here. And if we use like SHA, it was very, very expensive. So that was like the area without any SNARK-friendly hash functions. And now we go back a couple of years, so there's the timeline on the x-axis and the number of, I think it's rank 1 constraints on the y-axis, pretty sure, yeah. So we see that in this metric, if we count like proof efficiency in terms of constraints, we saw that SHA-2 is quite inefficient, SHA-3 is also inefficient, we didn't optimize for that, of course. And then we have this MIMSI cipher, some of you may know it. It wasn't designed for ZK, actually it was designed for MPC, but of course you can mostly use any permutation and turn it into a hash function using some symmetric mode. And this can also be done by MIMSI, and it turns out that in a ZK use case, it was actually much more efficient than SHA-2 and also much more efficient than SHA-3. And people started using MIMSI, which wasn't designed for ZK, but it was better at that time. And now we can flip the picture. Well, let's put MIMSI up there, which had roughly 2,500 constraints or something in this use case, like a simple hash evaluation. And then a couple of years forward, we had Poseidon, which was again much better. And now don't tell anyone, but Poseidon actually wasn't designed for ZK either. It's based on a block cipher which is called Hades MIMSI, which was focused also on MPC. So surprisingly, it turned out to be very efficient in ZK though. Well, all right. So cryptographically, this has led to a very new landscape, which started. I think this is very young. Started a couple of years ago. So we had a new setting suddenly. We had large primes. This is a nightmare for plane performance, which is part of the reason it's not really used in other parts of cryptography, of symmetric cryptography, sorry. And it's also a setting which is much less explored. So we're not as confident attack-wise with large primes than we are with like smaller fields. And also, we only had a single minimization goal, which was the number of multiplications. This is very wrong now. It's not true anymore. But at that time, we just tried to minimize multiplications. And lastly, in order to be efficient in these protocols, we had to focus on a very simple algebraic description, which again is not very good when designing a symmetric primitive. And this leads me to this sentence here. You should remember that. So if you want to design a symmetric primitive, then you should at all costs avoid any nice algebraic structure. But at that time, it was impossible to do that, right? So we had to do some algebraic structure in order to be efficient in these protocols. And well, that was part then of the reason that many of those hash functions got broken. We'll also come to that a bit later. And the changed landscape, attack-wise, was that algebraic attacks or algebraic cryptanalysis became the focus, particularly these nice or not so nice things like Gröbner basis attacks. This has been largely irrelevant in other parts of symmetric cryptography for years. But for this part of symmetric cryptography, it's like the main attack vector, suddenly. And interestingly, the statistical attacks, if you think about differential linear cryptanalysis and so on, those are very relevant, still very relevant for other symmetric primitives, but they're not so relevant here because mostly they can easily be avoided. That's a bit different now, but like a couple of years ago, that was the case. All right, so that's the history lesson. So what's happening now? That's more interesting, right? I started in the beginning with this use case where you have like a chain, you have non-chain proof, and you want to do this very efficiently. And for that, you need to use a hash function which is SNARK-friendly. Of course, today we have many more use cases, and one of those is recursive verification, where we use also hash functions or SNARK-friendly hash functions in different settings, not just for on-chain proving. This has led to new optimization goals, and in particular, it became apparent that the proof performance is very, very important in these cases. For like fast aggregation, you want to have a very, very fast hash function. And this means that the plane performance of the SNARK-friendly hashing suddenly became very, very important. Because, for example, when we designed Poseidon, we didn't really care about the plane performance. We compared plane performance with other SNARK-friendly hash functions, like I think Rescue and Vision at that time, but we didn't really compare to classical hash functions because we thought, well, you're circuit friendly, that's sufficient, and whatever plane performance you have, it's fine. That's different now, of course, very different. We also have new optimization techniques, so we had only the focus on rank 1 CS a couple of years ago, or 5 years ago when Poseidon came out. Now we have error, we have the many versions of Plonk. We have different fields, also in different state sizes, which is also very, very dangerous from the perspective of attacks. we also have new techniques in ZK. So we have lookup arguments, which are very nice because they allow someone to rather cheaply prove the truth of high degree, so the equivalence of high degree functions, which before was not really possible very efficiently. We have Fry, we have smaller fields, so you may know Plonky 2, 3, risk 0, a very nice technique, circle stacks, which makes FFTs over Mersenne primes very, very efficient. And I think Stu actually uses the circle stacks. But all those have very small prime fields, which also was not the focus years ago. And we have a very nice stuff also. We have BinUse, which essentially allows you to prove very efficiently on binary extension fields. This was possible before, so with binary extension fields, Fry is, I think, originally even defined over binary extension fields, but it wasn't very efficient, and BinUse makes it very efficient. And all these techniques have two main consequences for SNARK-friendly hashing, or for hashing in general. Firstly, classical hash functions became more circuit-friendly, because you could use these arguments here to make them more circuit-friendly. But on the other hand, circuit-friendly hash functions became much faster, because you could use things, for example, like lookup arguments to make them faster. And yeah, just a very quick overview. So all of those techniques, all of those varying prime fields, varying state sizes, and new proving techniques have led to a situation where we have a myriad of new schemes. We have some, like the older, more ones, the more classical ones, like Poseidon, Poseidon 2, and so on. We have these low-degree equivalent ones, which, many of those are broken actually. And we have the lookup table ones, which are arguably the most advanced ones, where we are very fast in plane and reasonably well also on the circuit side. And about attacks. So many of those got broken, and I'm not saying that all the others are secure. So for example, gmimc, I think it's so badly broken that if someone asks us what's the updated round number for gmimc, we just don't bother to answer because we don't know ourselves, it's broken. We shouldn't use gmimc. The others can maybe be fixed more easily. For example, Friday, very nice design, had some nice ideas which resulted in rescue, very cool. But Friday itself was broken pretty fast after its publication, and I think this was actually the first Gröbner basis attack in symmetric cryptography full round break since many years. And so this also seems to be the final boss at the attacks, the Gröbner basis. Essentially, if you're not aware, it's like a method for multivariate equation solving. There are many steps involved. There's like you first compute the Gröbner basis, then you have potentially to do some term ordering because the degree reverse lexicographical orders or other orders which are more efficient for the final step. And the final step is the solving, which, if you're very lucky, consists just in a root finding approach of a univariate equation. And the thing is that it's not so important here, but the thing is that there are many different trade-offs possible if you want to mount a Gröbner basis attack. So from the perspective of an attacker here, you can shift the complexity from one phase to the other. You can minimize either the variables, or you can try to minimize the degrees in your equation systems. You can also combine it with different approaches in symmetric cryptography. And it's very hard to think about all the approaches when you design a SNARK-friendly hash in order to be secure against Gröbner basis attacks. And for example, there have been many papers on Poseidon. It's still very secure against the attack as far as we know, but there have been quite some papers on that. And in general, there have been many. This is the plus side maybe of these attacks. There have been many new results in the last couple of years on Gröbner basis, and also new estimates which are more precise than the estimates we had 30 years ago. So I think this is pretty nice. And all these new use cases, especially aggregation, force us to be faster, right? We were not fast enough anymore with Poseidon, and so from our perspective, of course, the next target was SHA-3. Now everyone says, but SHA-3 is slow. It's not so fast, of course, but 5 years ago there was no hope to reach SHA-3 performance with any SNARK-friendly hash function, and now we can actually target that. And what about Blake? Well, that's our next target. It's going to be hard to break that. But we'll try, of course. And the main thing which helped here a lot is actually the lookup argument, which is pretty nice for our hashing. And so similar graph as before, but now on the y-axis we have the time in nanoseconds. We don't have the constraints anymore, so just plain performance. We start. So by the way, the orange dots are large prime instances, and the darker ones are small prime instances. And we see that Poseidon started to be quite slow at the beginning. It's gotten better due to like very smart people working for various companies optimizing it very nicely. So that started to get better. Poseidon 2 is a little bit better than Poseidon, and then finally in 2023 and 2024 we also managed to break the speed of SHA-3. So we're now, I think, at a factor 2 improvement compared to SHA-3, and that's pretty nice. So of course the question is, where do we go in the future? We want to go even lower. And as a bonus, so you can see that the large prime instances are quite slow, right? So if you're curious about that, there will be a talk at CK Summit 12 where we present a new hash, which is also very, very fast for larger primes. This hasn't been possible so far. All right, so we have the past, we have the present. What are the future challenges in this area? Let's start with the most boring one, cryptanalysis, but it's quite important still. So we have seen that some of the schemes were broken, but on the other hand, others had too much security. And I'm not talking about particular schemes now, but some of them have, for example, too much security against algebraic attacks, or the other way around, too much security against statistical attacks, and like barely enough security against algebraic attacks, or also the other way around. And I think it's very important to try to find optimal round functions which kind of balance the two types of attacks here. Of course, it would also be nice to have some stronger arguments, especially with respect to Grömer-basis attacks. That's something which, of course, probability in symmetric cryptography is something you try to avoid, right? You try to prove something secure based on some mode, but not on the primitive, because that's usually not possible. But it is possible to have strong arguments. For example, against statistical attacks, we have those using the AES arguments, white trace strategy, and so on. And it would be really cool to have those arguments also against a wider range of algebraic attacks. So that would help a lot also for the performance. Hardware acceleration, and these are some preliminary numbers, by the way. They're not final by all means, especially in the last row here. So if we want to have speed and performance, of course we want to have the best we can do, and the best we can do seems to be hardware acceleration. And for example, in the first row we see Poseidon 2 on a normal consumer CPU. And I'm not saying it's fully optimized. This can be optimized still a bit, maybe. It can also be parallelized, so you may get a factor 8 or something there, but you're still in this ballpark, right? And in the second row, we see the same on an NVIDIA 4 GPU, which is quite fast, so much faster than the CPU. And in the last row, we see the entire thing running on our Fabric GPU, which is by orders of magnitude better than CPU. So I guess this should be something we should also keep an eye on in the future. And by the way, this doesn't only apply to hash functions, but also to other components like entities and so on, which are very frequently used in many proof systems. So if we've seen that, maybe it's time to think about a different approach, because all the hash functions we've designed so far are CPU focused. We just did benchmarks on CPU, we chose instructions which are available on CPUs. Maybe we should think about new instructions which potentially are very slow on CPUs because they're not available, but which can be made available on a custom chip, right? So it should be much faster than on a custom chip. So maybe that's something newer. So this hasn't been done before. There are a few exceptions. For example, Vision Mark 32, which optimizes for hardware. It's used for recursive stuff in Binus, or can be used for that. But I think that's pretty interesting direction for the future to think about, like how can we actively use hardware to make new hash functions which are much faster than the existing ones. And there I think it's more realistic to go into the Blake region. All right, so not only that, not only hardware, but we also have new tools in cryptography. So we have small fields, I said this before. We don't know yet how all the hash functions actually, how they can be very fast for small fields, because we've a large amount of time we've thought about big fields only, in this area at least. And prime fields are not only becoming smaller, but they're also becoming binary extension fields, so very small to some extent. And the thing is, or the question from our perspective is, well, how can we use binary field structures in order to be much more efficient in hashing? And binary fields have a lot of advantages. For example, you have very, very easy subfield inclusions, and maybe you can more easily mix finite field sizes which you cannot very efficiently do for prime fields, in order to achieve an algebraic representation of the entire design, which is very complex and very hard to break. So this would also be an interesting direction for the future. All right, let me arrive at the summary. I'm only summarizing the future because it's the most interesting part, I think. So playing performance is crucial. We also need to be fast in the circuit, of course, but playing performance is very crucial. And I believe that we should get much faster than even like monolith and so on. I think that's a good goal for us. We also need to advance the understanding of algebraic attacks. That's being done by many people in the world currently, and I think that's also very important. We need to increase also confidence in existing designs. Like if we try an algebraic attack and we find it doesn't work on an existing design, it's also a nice result because we know that that it's secure against this vector at least. We also need to try to effectively use the new tools like hardware acceleration or novel proving techniques. And there are so many new proving techniques coming out every year. So I think that's also something we should keep an eye on. And something I didn't talk on about in this slide deck here is side-channel resistance. Now I'm not saying that side-channel attacks are a problem for secure proof systems or for those hash functions by any means, but like if we consider that these things potentially secure, protect like large amounts of money, we should also think about side-channel attacks and maybe like have an eye on that at least. And finally, of course, it would be very nice to start talking about standardization, and that's something that is not exclusive to SNARK-friendly hashing by any means. I think that standardization is something we should talk about also in the broader sense. So what about protocols or building blocks of protocols? How can they be standardized? I think that would be also very nice to have in the future. All right, and with that I'm done. Thanks.
So, thank you very much. I think we have a little bit of time for questions from the audience.
Yeah, thanks. You talk about optimization of these hash algorithms, and I'm wondering how much leverage there is at implementation detail, because even the perfect algorithm can be implemented badly, and you would see a lot of improvement if that implementation got improved. So, do you have experience in that?
Yes, indeed. So that's very true. Like for example, over the years, the Poseidon algorithm stayed mostly the same, right? But it got much faster. For example, there's an implementation in Plonky, I think, also in other projects, where you can do some things differently. For example, we in the original specification we had just like an MDS matrix, which is a certain type of matrix used for statistical attacks, so against statistical attacks. But we didn't specify how this matrix actually looks like. And it turns out there are certain matrices which fulfill the same properties, but are much faster or much better to compute, to multiply with. And for example, in Plonky they use NTT for that, because it turns out that if you use a circulant matrix, the entire thing is similar to a polynomial multiplication plus an evaluation step. So you can avoid the entire matrix multiplication by just doing two entities. And for some state sizes, this is much faster than the plain implementation. There are also other equivalences in the partial rounds of Poseidon we can use. And of course, there are things like if you're really good with processor optimization, with assembly and so on, there are a lot of stuff you can do. You can have the memory layout in a better way and so on. So there are many things that can be optimized, not just the algorithm, of course. Yeah.
So I guess this goes very much in the same direction when you look at the number of constraints, which was like the main metric to compare these hash functions, at least in the beginning.
Yep.
I mean, there's machinery to like optimize these constraint systems to make them smaller. Are these naive conversions to constraint systems? Are they already optimized, and what kind of exact constraints do you allow here?
Mm-hmm. So this was very primitive, let's say. This was just like a plain write-down maximum constraints. But if you think about stuff like custom gates, of course, in Plonk and so on, you can do this much more efficiently. And I would guess that a compiler does it very efficiently for you, maybe even better than if you do it.
Okay, but you wouldn't expect that the relative performance would change in any significant way?
No, it depends on the constraints, of course. So you still have to do the constraint evaluation, but no, I wouldn't expect so.
We would have a few more minutes, but if there are no more questions, I'm sure. Are you going to be around for today or tomorrow? Or
today for sure, tomorrow maybe also.
Maybe also. Okay, so you have more questions. I'm sure Markus will be happy to answer any more questions or have any more discussions about this topic. And with that, we conclude our ZK accelerated session. And we'll be meeting here again, so we're going to have a short break of around a little more than 20 minutes. And we're going to start again at 15:50 with Oana from Automata. She's going to be talking about using trusted execution environments in basically validity rollups. Yeah, so tune in for that.